Okay, this is the first of two videos talking specifically about tests of proportion. And we're going to emphasize in these videos, we're basically just looking at problems. And we're going to emphasize in this video the use of the calculator in step 3 and also in a particular hypothesis test function on the calculator that we have available to us. So let's just proceed directly to our set of problems. We'll work on two problems here. And the subsequent video, we'll work on an additional problem and a couple of other smaller problems. But let's look at this first one. Newspaper article states that of all misplaced cell phones found by people other than the owner, more than 60% of the finders tried to access owner's banking information. To verify this, a cell phone company found that of 750 found cell phones, 468 of the people who found them tried to access the banking information. Test at the 0.05 significance level that the newspaper article statement is true. You'll notice that I've highlighted in yellow the information that applies to the claim, and I've highlighted in blue or turquoise the information that comes from the sample that we'll need to calculate the test statistic. Okay, so we know what alpha is, 0.05. We know that the claim is back up here, more than 60%. We know that's P proportion. The value is 0.6, and we know the relationship is more than or greater than. So we've got our claim. We've got our alternate hypothesis, our null hypothesis, which is the assumed value, and we've got our alternate hypothesis, making this a right-tailed test. I'm not going to dwell on this. There's kind of an explanation over here, but we've covered this in the previous videos and previous notes. And then we we need to calculate the test statistic, which we do. We take the information from the problem, and we take the assumed value of the parameter P, which was 0.6, substitute that into the formula for Z, which is the test statistic formula for test of proportion. We discussed that before as well. And then we needed to, we looked at critical values. Okay, what we're going to do here is there is a calculator function that will help us find critical values, and it's called the inverse norm function. You can find it by hitting this second key and the bars key and then the number 3. And then it's going to ask us for a probability. The one thing that you're going to put in there is the less than probability, the area to the left of the given critical value that you're looking for. And it's going to be based upon what the significance level is, alpha. Left-tailed test, it's going to, if left-tailed test, we're going to be putting alpha in to the inverse norm function. Right-tailed test, we're going to be putting 1 minus alpha into that, because that would be the less than probability for that right critical value. And for a two-tailed test, we basically can put in half of alpha to get the left critical value. And then we can put in, and then because this is symmetric, we could also just basically find the critical value on the right being the opposite of the one on the left. Or we could put in 1 minus alpha over 2. And that would give us the area that will give us a critical value for a right tail. All right, this is a right-tailed test. So all of alpha is out in that tail. So we're going to put in 1 minus alpha into the inverse norm function. Let's take a quick look at the calculator. Let me clear this out. Clear the screen. Actually, just do a quit here. And so we want to go find inverse norm. Again, it's second vars number 3. And it's asking for the less than probability. Since alpha is 0.05, we can either put in 1 minus 0.05 and let the calculator handle the calculation, or we could have put in 0.95, which is 1 minus 0.05. I'm going to close the parenthesis and hit enter, and there we have the critical value for the right, 1.645 to 3 decimal places. You might recognize that. If alpha is 0.95, which is probably the most common alpha, it's either 0.95 or 0.01, but 0.95 has a right tail of 1.645, a left tail of negative 1.645 for one-tailed test. For a two-tailed test, it would be negative 1.96 and positive 1.96. All right, so let's stop that and come back to our problem. And now let's look at the other method in step 3, and that is calculating the p-value. And the p-value is a probability. Remember, the probability of observing a test statistic that is more extreme, which means farther from the mean, than the one that was observed in the test statistic. So basically what you would end up with is finding the area underneath the curve farther away from the mean than the test statistic. If it were a two-tailed test, as you'll recall from previous notes, then we would, whichever side the test statistic falls on, whichever side of the mean it falls on, you'll find the area underneath the curve farther away from the mean, and then multiply that area by 2 to get the p-value. If it's a one-tailed test, you'll just find the area underneath the curve farther from the mean, whichever side it's on, and that is the p-value. You don't have to multiply it by 2. But we can use a calculator to find those areas. And to find an area underneath the standard normal curve, the z, we are going to use the normal CDF, which is found at second vars again, and this time number 2. And let's talk about that. Let's go look at the calculator and let's talk about what goes into it. Let's go find second vars and the number 2, normal CDF. All right, so what is normal CDF asking for? It's asking for 2 things. It's asking for basically the boundaries for our area underneath the curve. Remember, what we're finding is an area underneath the curve farther away from the test statistic. Well, the boundaries are, if it's on the left tail, the boundaries are negative infinity on the left and the test statistic on the right if it's left tail. But we're just going to, instead of negative infinity, we're just going to put in a large negative number. If it's a right-tailed test, then we are going to find the area underneath the curve farther from the test statistic, farther from the mean than the test statistic. So the boundary starts at the test statistic, which is the left boundary of that area, and it goes up to a positive infinity, so a large positive number. And if it's a two-tailed test, we will do the following. And we're going to be looking at a problem, and each one of these problems is either left tail, right tail, or two tail. We're going to be looking at all 3 across these 2 videos. So let's go ahead and look at our right tail test, which is the one we're looking at. And our test statistic is our bound on the left bound of the area. So it's going to be 1.34. That's the left bound of the area underneath the curve to the right of our test statistic, our critical value. Test statistic, and a comma in between and then a very large number on the right. So those are our boundaries for a right-tailed test, the test statistic, comma, and a very large number. Right-tailed test, okay? Test statistic, comma, right-tailed number. Hit enter, and we get 0.0901. And that is the p-value because it's a one-tailed test. So let's go back to our okay. So here we have, this is exactly what we just did here. And this is a picture of what we were looking at. Area underneath the curve from left, from 1.34 up to positive infinity. Okay, so that gives us, we've got our critical values, and we looked at where the test statistic fell relative to that critical value. And if it did not fall in the rejection region, meaning farther from the mean than a particular critical value on that side, and then we're determining what the size of the p-value is, and we compare that to alpha. And remember what the rule for rejecting is. If the p-value is less than or equal to alpha, we will reject the null hypothesis. So we know here that we're not going to reject the null hypothesis in either case, for critical value approach or p-value approach. And so we make that statement and we state why. The p-value is bigger than alpha, and the test statistic is not farther away from the mean, not greater than, if it's farther away from the mean, it would be greater than 1.645, but it's not in the critical region. And then we make our statement of conclusion using the flow chart that I showed you in a previous video. And then the last thing we want to look at is there is a hypothesis test for proportion on the calculator that we can use, and you probably will be using. And the tests, hypothesis tests on the calculator give us two things. They give us as output the test statistic value, so we don't have to calculate it directly, and it gives us the p-value. It does not give us, it doesn't have anything to do with critical value. It's only a p-value. So it covers step 2, test statistic, and it covers step 3, p-value. And we make our decision based on the p-value then, and then state our conclusion. So the test on the calculator for test of proportion is called the 1-prop-z test. And to get to it, you hit the stat button, right arrow to tests, and go down to 1-prop-z test, and then hit enter. And then it's going to show you a screen for inputs, and then you can get your results after you've entered that and hit either calculate or draw. So let's go look at the calculator. And I need to remember that X is 468 and N is 750. And our proportion assumed value is going to be 0.6. Okay, so let me clear this out, and let's go look at, and where do we find the test of proportion, the 1-prop-z test? We hit stat, and we go right arrow over to tests, and then we're going to, the one we're looking for is number 5. So if you just remember test of proportion, it's number 5. So we hit number 5, and then we get 1-prop-z test. It wants to know what our test proportion, assumed value of the proportion is, and it is 0.6. So I'm just going to type 0.6 there. And X was, I think it was 468. But let's double, yeah, 468 and 750. So 468. And 750 is the number of trials. Oops, let's go back and delete that extra 0. and the alternate hypothesis relationship. In here, P0 is the assumed value, so you're going to get that from the null hypothesis, H0. And prop is the alternate hypothesis. This was the null hypothesis, I'm sorry. P0 comes from the null hypothesis. And the alternate hypothesis is gives us the relationship, and it was greater than, so it's already highlighted, and we hit calculate. Oh, so we got to hit enter. Let's go, sorry. And then we go down to calculate. And we get a test statistic value, 1.34, which is what we had, and a p-value. The area underneath the curve farther to the right is 0.0899, rounded to 4 decimal places. Okay. And so that would be test statistic, and p-value. You would use the p-value, then compare it to alpha to come up with, make your decision. So let's stop sharing here. We got 0.0899. Let's see if I have that correct in 0.0899. Okay. So that's how we would use this function. It's second vars, or not second vars, stat, right arrow to test, number 5. Okay. All right, and then we would basically continue on with steps 4 and 5 after we've done this. We still have to do step 1. We still have to do 4 and 5. This only gives us information from step 2, the Z, and step 3, the p-value. Okay. All right, so let me stop sharing that, and let's go back to, oops, I'm sorry, we were there. Okay, we've done this first one here, and I'll tell you what I'm going to do. I'm going to stop there, and we'll probably extend this to 3 videos, but we'll do another one similar to this. So let's end this video here, and we'll pick it up. We'll pick the second test up in the next one.